All right, Chem 2, practice quiz 3. So we're looking at this and we're using the Clapeyron equation, which allows us to compare the vapor pressure and the atmospheric pressure to get the boiling point changes. All right, so first step we want to do is look at the atmospheric pressures and realize that boiling point is when the vapor pressure equals the atmospheric pressure. Right. And so I've got my Clapeyron equation. The first one up, they gave me delta H vaporization, but it needs to be in joules per mole. So I'm going to have to convert that over to from kilojoules to mole. So I'll get 40,700 joules per mole. R is going to be an 8.314 joules per mole. So that's why I had to go to joules. You can actually use torr or atmosphere for your pressures, but they've got to both be the same. All right, both the same units. And then you want to be real careful about your T1 and your T2 versus your P2 and P1. Make sure you keep those together. So when I look on here, it says 520 is the typical pressure, and they want to know the boiling point at that. So I'm going to make that P2, and my P1 would be 760, which is our normal atmosphere, our standard, and then 100 degrees Celsius is what we look for in water. And so that's what we're going to be using here. So I went ahead and took everything to Kelvin, and then I did a bunch of math, mostly just sticking this in, and then solving for T2, and I came up with 363.7. Some of the key points that students tend to miss, not only do we have to make sure everything's in the right units before we do it, here I had to take the negative of both sides, and then I also did the inverse by just taking my answer and doing 1 divided by that. So I just did 1 divided by 0.002757, and that gave me my product. That makes sense, 362 Kelvin. Makes sense, and it's actually less than my temperature that I would expect for boiling water. So that makes sense. We're at a lower pressure. It'll be a lower boiling point. And that diethyl ether is a really low boiling point, and it was used as an anesthetic. It's actually a pretty cool story. A doctor was invited to, a medical student was invited to a party, and he showed up, and people were waving around ether rags, soaking rags in ether, and they'd get really, really high. And so he showed up to this party and was in a classroom, and the students were running around, and one of them popped a leg on a desk and was bleeding pretty badly, but it didn't stop them. They were still running around. So that's how that medical student figured out that it was a pretty good anesthetic. We no longer use it because it has a real high vapor pressure, and it's highly flammable. So that means that even just a candle can be dangerous. We also have a big problem with it because the dosage it takes to knock you out and the dosage it takes to kill you are way too close. And so that's one of the other reasons we've got new anesthetics. We don't use that anymore. So I'm using the Clapeyron again. So I've got the pressures they gave me. I've got R, and I need to make sure that I've got my temperatures in Kelvin. I'm solving for H, and H needs to be in joules when I get done with this, but I will also go and get into kilojoules. So I'll type that into my calculator, type this into my calculator, and then I'm going to divide both sides by this 1.86, and then I'm going to multiply both sides by 8.314. So 28,622 joules per mole. That seems like a lot, but remember when we were up here, for water it was 40,700 joules per mole. So this is only 28.6 kilojoules per mole. So that's actually acceptable. As the temperature increases, the vapor pressure will increase. So the vapor pressure is the pressure of the gas above a liquid at a given temperature. Okay, so last practice quiz for chapter 10. We've got phase diagram here, and we want to identify the parts. So first thing I do when I look at these is remember that pressure, a low pressure, and a low boiling point, they come together here. And so if I'm at a low temperature as I go left to right, I'm going to go from a solid to a liquid to a gas. Okay, so phase 3 here is my solid, then I have liquid, and then gas. Okay. This one is marked because 1 atmosphere is our standard. So this would be marked would be my standard melting point and my standard boiling point. And so again, remember temperature gets bigger as I go from left to right. That helps me keep up with my solid, liquid, and gas. Number 4 up here is supercritical fluid. So if I'm on the red line between 3 and 2, for instance, where this B is, if I'm on that red line, I have some solid and some liquid present. If I'm on the red line over here, I have some liquid and some gas present. If I am in the middle at this point D, that's called the triple point, I will have all 3 present. So I'll have solid, liquid, and gas all present there. We're also going to be looking at A, which is the critical point. And so anything above that, we're going to be looking at supercritical fluids, which behave kind of as a mixture between gases and fluids. All right, let's talk about our phase changes. So going from a gas directly to a solid is deposition. Going from a solid to a gas is sublimation. Going from a liquid to a liquid to a solid, we've got freezing, and then going the other way, we got from a solid to a liquid, we got melting. And here I'm going from a gas back to liquid, so condensation. And then going forward, I have vaporization. We also call it boiling or evaporation. And so that's what they're looking at, going from a liquid to a gas. So if I change these pressures, I can come across and find the new melting point and the new boiling point. So that's what the rest of this is all about, labeling, and we will give you one of these and ask about it. Thank you.